Okay, let's get started with putting this all together. We want to take our complex ions and figure out if they are paramagnetic and therefore colored using the crystal field theory. So we have our questions here. This question says, how many paired, unpaired electrons would you expect from the complex ion? So we're dealing with unpaired electrons. We have a complex ion. This complex ion is here. It has its charge. And so we have to make sure that we're relating oxidation state of the metal ion, electron configuration of that metal ion, and then, of course, using that to get the number of electrons that are going to be used in our d orbitals. Now, of course, those d orbitals are going to be splitting based on the ligand that is attached to our metal ion. And we can use the spectrochemical series to help us figure out if it's going to be large crystal field splitting or if it's going to be small crystal field splitting. And that's then going to help us understand that these ligands are going to have high spin or low spin. So you're going to be high spin if you have a weak field ligand and low spin if you have a strong field ligand. And that's going to help us understand how those d orbital electrons are filled in our split d orbitals for these different complex ions. So as you can see, we kind of just went through to break down what unpaired means, what the complex ions mean. So let's go ahead and get some of these details. First things first, we want to get the oxidation number. So we have CO, OH, okay, 6, 3 minus. To get the oxidation number of this cobalt here, we're going to add that as X. We know that we have 6 OHs, which we know are going to be OH minus. You can go ahead and look at the ligands, see whether they're monodentate or bidentate, and also their charge from that overall ligand page that you're given for your practice exam. And you're also given the spectrochemical series to figure out if you have a strong or weak ligand. Okay? So this entire thing is going to be -1. So instead of just writing OH minus here, I'll just write the specific charge. And that whole thing is going to equal to 3 minus. So we have X minus 6 is equal to 3 minus. And so X is going to equal to plus 3. That means we have a cobalt that has 3 plus. And so what we have to do is go further because we want to know the amount of electrons that this cobalt 3 plus is going to give us in its d orbitals. So I have to make sure that I am basically taking my cobalt 3 plus and completing the electron configuration for it. So you go on the periodic table, you get your cobalt. So that's going to be our argon, and then we're going to have 3d6. Okay, so that means we're going to have 6 electrons in our d orbitals. So the first thing we do is have to get our oxidation, then we're going to get our electron configuration, then we're going to fill out those d orbitals. But we need to make sure that we know how to fill out those d orbitals by looking at the ligand. Okay, so in order to do this, we have to look at our ligand. We see that we have OH minus. OH minus is going to be a weak field ligand, so we are going to have high spin. High spin means that we have to fill the electrons, 1 electron in each of the orbitals first before we pair them up. So we have 6 electrons, so that means we're going to have 1, 2, 3, 4, 5, and 6. So when they ask us how many unpaired electrons we have for this question, we have 1 here, 2, 3, 4. And so our answer would be 4 unpaired electrons for this complex ion. Now, of course, you can go further, and I always recommend when you're doing practice to always go further. What else does this mean? It means that you have 4 unpaired electrons. It also means that you will have something that is going to be paramagnetic, which means it can have color, right? It also means that because we're dealing with weak field ligand, you have absorbed low energy, and you also have absorbed long wavelengths. Okay, so it's like all these little details we can start adding in. And you can also say, because this is a weak field ligand, that it is going to have a small crystal field splitting. Okay, so let's go ahead and get into the next example. We want to know how many unpaired electrons we have for this particular complex ion. So first, we're going to take our complex and figure out the oxidation for our iron. So we have X plus 0 is equal to 2 plus. So we actually are going to have Fe2 plus here. And the next thing we need to do is get our electron configuration for this Fe2 plus ion. So we have argon 3d6. Next, we are going to build up our d orbitals, and we're going to use the ligand attached, which is the NH3 ligand, to figure out how we're going to fill those 6 electrons in these d orbitals. So NH3 is here. It is a strong field ligand, so that means it's going to have low spin. That means that when we're filling these orbitals, so let's go ahead and do that. We have 6 electrons. We have to make sure we pair up the lower energy orbitals first before we move to the higher energy. So we have 1, 2, 3, 4, 5, and 6. So as you can see, everything is paired up here. And because we have low spin, we can end up saying that we have no unpaired electrons. So 0 unpaired electrons, 0 unpaired, meaning that this is going to be diamagnetic and have no color because it is all paired up. There is no color because we have everything paired in these orbitals. Also, we can go ahead and get further information about our strong field ligand. Strong field ligand means that we're going to have a large crystal field energy splitting. We're also going to absorb shorter wavelengths that are higher in energy. So of course you can start adding all these little details just by doing these examples. Let's do one more. This question, they're saying iron forms a complex in hemoglobin. For each of the 2 octahedral complex ions, here's one here and one here, draw an energy diagram showing orbital splitting and predict the number of unpaired electrons and identify the ion as low spin or high spin. So that's a lot to unpack. So you want to make sure you're kind of breaking down each portion, okay? So I'm just kind of underlining. I'm like, okay, octahedral, we know where the complex is. They want us to do an orbital splitting diagram, which they tell us to predict the number of unpaired electrons, just like we did before, and then identify as low spin or high spin, based on the type of ligand that is attached to each of these complexes. Okay, so the first thing I want to do is basically draw the energy diagram. I have my arrow, which is going to represent energy here, and then I have my d orbitals to show that these are going to be lower in energy than these that are higher in energy, okay? Then I'm going to predict the number of unpaired electrons by first getting the oxidation number for each of my ions here. So this water is monodente and it's going to be neutral. So this is simply going to be Fe2+. That means we're going to have argon and then 3d6 here. Also, we're going to have X minus 6 is equal to 4 minus. So this is also going to be Fe2+, which is simply going to, again, be argon 3d6. So we have 6 electrons to kind of work with. And now we want to fill these electrons based on whether or not they have high spin or low spin, which is one of the things they wanted us to identify as well. So that's going to be based on the ligand that is attached to our metal ion. So here we have water, which we know is going to be a weak field ligand. So that has to have high spin. And then here we have our Cn minus or cyanide, which is going to be a strong field ligand or low spin. So let's go ahead and fill our electrons. High spin means we have to fill out all the orbitals first. So we have 1, 2, 3, 4, 5, and 6. Low spin means that we have to fill all the lower energy orbitals first before we go to a higher energy. So we have 1, 2, 3, okay, 4, 5, and 6. Now, what else do they want us to do? So we have wrote our energy diagrams. We've done that. We've identified high or low spin. Now they want us to tell us the number of unpaired electrons. So for this compound, we have 1, 2, 3, 4 unpaired electrons. Okay, so 4 unpaired here. And then here we have no unpaired electrons. So we can go further, just like everything else, and say no unpaired electrons means you are diamagnetic. Also, we have a strong field ligand, so that means you are going to absorb high energy or short wavelength, okay? Photons of light. You also are going to have a larger crystal field splitting, so you can kind of write all these little details down when you're doing these type of problems. And then over here, we have a high spin based on a weak field ligand, which is water. There are going to be 4 unpaired, so this is paramagnetic and has the ability to be colored, okay? So because of that, it's going to also have a small crystal field splitting. It's going to absorb low energy or long wavelengths. So again, this is how we kind of are bringing this all together and to connect this. And you want to just continue to do more practice problems from here, the textbook, your homework, practice exam as well, to help you get oriented with how to organize yourself with this information.